Hello everyone, my name is Niti from BSc Chemistry Honors first year. My roll number is 44. So here we are start our chapter which name is covalent bond. So start from topic first, resonance. It has already been studied in earlier classes that the concept of resonance or mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more covalent valence bond structure, each of which can explain most, but now all the observed property of the compound, the actual structure lies somewhere in between the various possible covalent structure. The various possible structure are called contributing or conical structure, and the actual structure is called resonance hybrid. The resonance hybrid is indicating by putting a double-headed arrow between the contributing structure. The concept of a hybridization of two or more conventional value bond structure to arrive at a entirely new and individual structure, which however can be depicted on paper in the term of a conventional formula, is termed as resonance. One of the most well-known examples of the application of resonance is afforded by benzene, since benzene could not be assigned any satisfactory valence bond structure which could explain all its property. It was proposed that benzene is a resonance hybrid of structure 1 and 2, which is shown below in the diagram. So now this implies that the structure of benzene is represented neither by first and second but lies somewhere in between of the two. It is evident that in the resonance hybrid the bond which link the carbon atom neither respond to single nor double bond. On the other hand, all the bonds are equivalent and are intermediate between single and double bonds. This has been confirmed by X-ray diffraction studies which show that all the carbon-carbon bond in benzene are of actually the same length, which is in between that of carbon-carbon single bond and carbon-carbon double bond. The resonance hybrid structure of benzene has 151 kilojoule per mole of energy less than either of the contributing structure. This represents the resonance energy of the molecule. It is that energy which is responsible for usual stability and remarkable behavior of benzene. So now it's noted that the concept of resonance does not mean that any one molecule of benzene spend a part of its time in structure 1 and the rest of time in structure 2. It also does not mean that some molecule of benzene has get structure 1 and other has get structure 2. Which resonance mean is that any one molecule of benzene always have the same single structure which is identical with that of any other molecule and is intermediate between structure 1 and 2. Other example of resonance. First one is carbon dioxide. Carbon dioxide is considered to be resonance hybrid of three contributing structure as shown below. As you see, the observed bond length of carbon oxygen bond in carbon dioxide, which is 115 picometer, is lesser than that the carbon oxygen double bond 122 picometer, but which can be justified in terms of its resonance hybrid structure. Second one is carboxylic acid. The acidic structure of carboxylic acid is explained by treating the carboxylic acid as the resonance hybrid of the following contributing structure, as you see. And third one is 1,3-butadiene. 1,3-butadiene and other conjugated dienes also exist as resonance hybrid. For example, 1,3-butadiene is a resonance hybrid of three contributing structure. Use of curved arrow to show interconversion of contributing structures. Since contributing structures differ from each other only in the position of electrons, curved arrows are often used to show the flow of electron in conversion of one structure into another. This make it easier to draw the various contributing structure of a given species. For example, the contributing structure of carboxylic acid may be drawn as shown below. Similarly, the contributing structure of 1,3-butadiene may be shown as below. Condition for resonance. According to general theory of resonance, the various conventional structural formula contributing to the structure of resonance hybrid must satisfy the following condition. First, the various contributing structures should differ from each other only in the position of electrons, pi electron and lone pair of electrons, whereas the relative arrangement of atoms or atomic nuclei to be more precise and their state of hybridization must be same. Note, it may be recalled that existence of structure having the same molecular formula but different relative arrangement of atomic nuclei leads to phenomena of isomerism. The atom involved must lie in the same or nearly the same plane. The number of paired and unpaired electrons in each contributing structure must be the same. For example, CH2 single bond CH double bond CH single bond CH2 is not valid contributing structure for butadiene since it has more unpaired electrons than other contributing structure. All the contributing structures must show the correct answer of valence electrons. For the element of second period, no contributing structure should have more than 8 electrons in the valence shell of element. For example, CH2 single bond CH double bond NH3 cannot be considered as contributing structure since in it nitrogen has 10 electrons in the valence shell, which is not possible. All the contributing structures should have the same or nearly the same amount of energy and stability. When the contributing structure differ in energy content or relative stability, the more stable structure make greater contribution toward the resonance hybrid. In determining the relative stability of contributing structure, the following point may be noted. First one is the larger the energy of covalent bond in a structure, the greater the stability. For example, as you see, second one is the structure involving representing of positive energy charges are less stable than which do not involve any separation of charges. Third one is when atom of different electronegativities are involved, the structure having negative charge on more electronegative atom and positive charge on less electronegative atom are relatively more stable than the other way round. For example, fourth one is the structure having large charges on adjust atom are highly unstable. Eighth, the number of contributing structure, the more stable is resonance hybrid. Now let we study about the property of resonance hybrid. First one is stability. A resonance hybrid is always more stable than any of contributing structures. The extent of greater stability of resonance hybrid depend upon the number of contributing structure and their relative stabilities. Resonance energy. It is measure of a stabilizing due to resonance and may be defined as the difference in energy between the energy of resonance hybrid and its most stable contributing structure. Greater the resonance energy, greater is the stability of resonance hybrid. For example, the resonance energy of benzene is about 151 kJ per mole. The value of resonance energy can be determined from the data involving heat of hydrogenation and heat of combustion, etc. Bond length. In a resonance hybrid, the bond length are different from those in contributing structures. For instance, the carbon-oxygen bond length in carbon dioxide is 1.15 angstrom or 115 picometer as against the value of 1.22 angstrom or 122 picometer for a carbon dioxide double bond length. It may be seen that the concept of resonance hybridization is essentially equivalent to delocalization of electrons. It is delocalization of electrons which leads to formation of stronger bond and more stable molecule. Therefore, the term delocalization energy is often used in place of resonance energy. Resonance effect. It is process of permanent displacement of electron in a molecule brought about the resonance or mesomerism, generally designed as R or M effect. Unlike inductive effect, resonance or mesomeric effect is transmitted through pi electron and operate in unsaturated system, particularly those containing a suitable atom or group in conjugation, which unsaturated system. For this reason, it is also termed as conjugative effect. A given atom or group is said to be conjugation with an unsaturated system if it is directly linked to one of the atom of multiple bond through a single bond. For example, in the case cited below, the group G is in conjugation with carbon-carbon double bond. What happens in that resonance effect causes delocalization of electron and give rise to additional contributing structure due to withdrawal or release of electron by given group. For example, in the molecule CH2 double bond CH2 single bond CH double bond O where contains C double bond O group in conjugation which C double bond C. Electron withdrawal by C double bond O group causes delocalization of electron and give rise to the additional structure as you shown below. Type of groups involved in resonance and their resonance effect. First one is group having electron withdrawing resonance effect, R or M effect. Groups such as NO2, C double bond O, C triple bond N, SO3H and COOR withdraw electron from an unsaturated linkage through resonance and are said to have M or R effect. For example, structure given group having electron releasing resonance effect plus R or plus M effect. Groups such as OH, OR, NH2, NHR and NR2 which can release electron through resonance are said to have plus M or plus R effect. This group have one or more lone pair of electron which they furnish for conjugation with the unsaturated system. For example, vinyl chloride. For example, vinyl chloride. It is important to remember that unlike inductive effect, resonance effect suffers practically no difference in intensity with the increase in distance along the chain of atom. Application of resonance effect. Resonance effect is very useful in explaining the stability, ease of formation and reactivity of many chemical species as illustrated below. First, low reactivity of vinyl halide and aryl halide as compared to alkyl halide and vinyl halide exhibited very low reactivity in nucleophilic substitution reaction. This is because the halogen atom in vinyl halide causes delocalization of electron due to plus R effect and give rise to an additional contributing structure as shown below. Due to resonance stabilization, the halogen atom gets more firmly attached to carbon and is not displaced readily. Similarly, low reactivity of aryl halide toward and nucleophilic substitution can be explained in terms of resonance stabilization. Acidity of carboxylic acid. The acidic nature of carboxylic acid is due to their ionization aqueous solution to form carboxylate ion and hydronium ion. The carboxylate ion is stabilized by resonance due to minus R effect of C double bond O group. This makes formation of ion easily possible and is mainly responsible for acidity of carboxylic acid. Even in undissociated carboxylic acid, resonance is possible, but this involves separation of charge. As such, it is much less effective than in carboxylate ion, where the resonance forms are identical. Therefore, carboxylate ion is stabilized by resonance due to greater exhibit than carboxylic acid, which explain the tendency of carboxylic acid to undergo ionization. We will encounter many more examples of resonance effect in explaining the ease of formation, relative stabilities, and relative relatives of many species during the course of our study. valence bond theory, which is most important topic. The valence bond theory are put forward by W. Whittler and F. London in 1927. It was improved that extended by L. Pauling and J.C. Streller in 1931. The basic assumptions of this theory are atoms do not lose their identity even after the formation of molecule. The bond is formed due to interaction of only the valence electron as the two come close to each other. The inner electron do not participate in bond formation. During the formation of bond, only the valence electron form each bonded atom their identity. The other electron remain unaffected. The stability of bond is associated by the fact that the formation of bond accompanied by release of energy. The molecule has minimum energy at a center distance between the atom known as intermolecular distance. Larger the distance energy, stronger will bond formed. Main limitation of valence bond theory are the valence bond treatment could be applied successfully to only a few simple system. In most of the system, the mathematic treatment involved it is very important and we have to use approximate method. Therefore, valence bond treatment is inadequate in many systems. This theory assumes that the two electrons of a shared pair contributing the internuclear bond must common from two different atoms. Therefore, the formation of coordination valency could not be explained by this method. It failed to explain bonding in electron deficient compound. For any molecule or ion, we have the right several resonating structure and even then we say that the true structure is known of this but a resonance hybrid of this structure. It is not possible to write one structure which can explain all the structure feature of that molecule or ion. According to this theory, the atom in the molecule of oxygen should have electric configuration resembling neon. This would make the molecule diamagnetic as you show. However, oxygen molecule is paramagnetic, indicating the presence of two unpaired electrons. This theory failed to explain the paramagnetism of oxygen molecule. Though valence bond theory has some limitation, yet it find wide application. It is frequently used as qualitative guide in predicting the geometry of molecule of ion. Essential characteristic of covalent bond. The covalent bond is localized between the nuclei of atom. The strength of this bond and upon the exchange of electron between the two combining atom. It has been shown Pauling that the strength of covalent bond is proportional to amount of overlap of have function or atomic orbital of two electron contributing the bond. The bond formed be strong if there is maximum overlapping of atomic orbital and there is maximum subtraction of charge densities of electron involved in bond formation. Thus, the bond formed by a given orbital will tend to lie in direction in which that orbital has maximum bond. In other words, the covalent bond has directional nature. The directional nature of covalent molecule lead to definite shape and geometry. The shape and geometry of molecule can be explained on the basis of two theories: hybridization, valence shell electron pair repulsion, which is known as VSEPR theory also. Hybridization. The concept of hybridization is introduced to explain the shape of molecule. We have meant that the formation of a covalent bond require one unpaired electron with each of two overlapping orbitals. This means that the number of bonds formed by an atom depend to some covalent on number of unpaired electrons in the atom. Therefore, in accordance with the electronic configuration, beryllium is accepted to be inert, no unpaired electron and no bond pair with one unpaired electron should be monovalent. one unpaired electron, one bond, and carbon one s2 2s2 2p2 with two unpaired electrons should be divalent. Two unpaired electrons, two bonds. However, in their compound, beryllium is divalent. Example BeF2 BeH2. Electron is trivalent. Example BF3 BH3, and carbon is trivalent. Example CH4 CCl4. Therefore, it is not possible to account for the valencies of Be, B, and C on the basis of theory of bonding. In order to explain this anomaly, a new concept known as hybridization was introduced. This can be explained by taking the example of carbon compounds. The ground state electronic configuration of carbon, which is Z equals to 6, is 1s2 2s2 and 2p6. The outer electron configuration of carbon may be represented as: there are only two half-filled orbitals in the valence shell of carbon, therefore its bond capacity should be 2. However, in actual practice, carbon exhibits the bonding capacity of, for example, it is known to form molecules such as CH4, CCl4, etc. This can be explained on basis of promotion concept. In order to explain the bond concept of carbon, it was proposed that one of the electron from 2s filled orbital is a promoter. The 2p empty orbital 2pz, which is higher energy state. This state of atom is known exhibit state, and the process is known as promotion. Thus, four half-filled orbital get force valence shell, which account for bonding capacity of 4 of carbon. The configuration carbon is exhibited state. Represent of carbon is excited state as you shown below. The above configuration reveals that all the four bonds formed by carbon will not be identical. For example, in the formation of CH4 molecule, one CH bond will be formed by overlapping of 2s orbital of carbon and 1s orbital of hydrogen, whereas the other three carbon hydrogen bond will be formed overlapping of 2p orbital of carbon and 1s orbital of hydrogen. But actually, in most of the organic compounds such as methane CH4, carbon tetrachloride CCl4, etc., all the four bonds of carbon are equivalent. The equivalent character of the carbon can be explained with the help of a new concept known as hybridization. This may be defined as the phenomena of mixing of orbital of slightly different energies so as to redistributed energies and to give new set of orbital of equivalent energies and shape is called hybridization. The promotion of electron from 2s to 2p of higher energy level will require an input of energy. Where this energy come? We know that the formation of covalent bond is accompanied by release of energy of reaction. Thus, reacting atoms, say hydrogen atom, approach a carbon atom to form covalent bond. Energy is released. This energy released is used to promote one of the 2s electron into an empty 2pz orbital. The new orbital formed as result of hybridization are called hybrid or hybridized orbitals. To form four equivalent bond, one 2ps and three 2p orbital of carbon hybridize and form a new orbital called sp3 hybrid orbitals. The hybrid orbital form have characteristic orientation in space. For example, the 4sp3 hybrid orbital oriented toward the four corner of regular tetrahedron. These four orbitals overlap with 1s orbital of hydrogen to give four equivalent bonds. It may be noted that hybridization is not a real physical process, but it is mathematically concept which has been introduced to explain the structure property of molecule. Characteristic of hybridization: the number of hybrid orbital formed is equal to the number of orbital that get hybridized. The hybridized orbital are always equivalent in energy and shape. Third one is the hybrid orbital are more effective in forming stable bond than the pure atomic orbitals. Fourth, the hybrid orbital are directed in space in some preferred direction to have stable arrangement. Therefore, the type of hybridization give the geometry of molecule discussed later on. Condition for hybridizations are only the orbital present in valence shell of atom are hybridized. The orbital undergoing hybridization should have only a small energy difference. The orbital which greatly differ in energy cannot take part in hybridization. Promotion is not an initial condition prior to hybridization. It is not necessary that only half-filled orbital participate in hybridization. In certain cases, even filled orbital of valence shell participate in hybridization. Uses of hybridization. There are some type of hybridization. This is not only involve s and p orbital but d orbital. The different type of hybridization are discussed below. Sp hybridization. In sp hybridization, one s and one p orbital mix and form two equivalent sp hybrid orbital. Linear geometry of molecules such as BeCl2, BeH2, BeF2 can be explained on basis of sp hybridization as described below. Beryllium, whose atomic number is 4 in ground state, has electronic configuration 1s2 2p2 as shown below. According to valence bond theory, the formation of covalent bond require one unpaired electron with each of two combining atoms. This means that the bonding capacity of an atom depend upon number of unpaired electron in the atom. Therefore, beryllium is expected to no valence because there are no unpaired atom in its atom. However, beryllium exhibit valency in its compounds such as BeH2, BeF2, BeCl2, etc. sp2 hybridization. In sp2 hybridization, 1s and 2p orbital hybridize to form three equivalent sp2 hybrid orbitals. This can be illustrated by considering the example of BF3 molecule. Shape of BF3 molecule. The electronic configuration of boron is B equals to 1s2 2p2 2px1. The electronic configuration of B is represented in figure number 6. Since boron is trivalent in compound, it is assumed that one of the two s orbital electron is promoted to next vacant 2p, that is 2py orbital. Therefore, the excited state of boron has three unpaired electron. Now, to form three equivalent bond, the three equivalent orbital 2s 2px and 2py hybridized to form the sp2 hybrid orbital. This three sp2 hybrid orbital, trying to remain as far as apart as possible, adopt a normal planar arrangement making an angle of 120 degree. The mixing of three atom orbital 1s 2p and 2p is shown in figure 7. These three hybrid orbital formed are directed toward the three corner in equilateral triangle. Each of this sp2 hybrid orbital has 1/3 s character and 2/3 character. sp3 hybridization. In sp3 hybridization, 1s and 3p orbital hybridize to form 4 sp3 hybrid orbital may be illustrated by considering the formation of CH4 molecule. The carbon in ground state, which atomic number is 6, 1s2 2p2 2px1 2py1, has only two unpaired electrons, account for trivalency. It is assumed that one of the 2s electron is promoted to vacant 2p electron. To account for equivalent carbon hydrogen bond, 1 2s and 3 2p hybridize to form 4 sp3 hybrid orbital. These are shown in figure 9 as you show. In this figure, sp3 hybridization of carbon atom in the formation of methane molecule, the mixing of 4 atomic orbital 1 2s and 3 2p is shown in figure 10a. These 4 formed are directed toward the corner of tetrahedral in formation of methane molecule. Each this hybrid orbital overlap with 1s orbital of hydrogen to form 4 carbon hydrogen bond. This methane molecule has tetrahedral geometry with each bond angle of 109 to 28 or 109.5 degree as shown in below figures as you see. Fourth one is sp3 hybridization. This involves the mixing of 1s, 3p and 1d orbital. The geometry of pf5 can be explained on the basis of sp3 hybridization. The outer electronic configuration of phosphorus. The central atom is 3s2 3p3, which may be represented as in figure 11a. It has 3 unpaired electrons in ground state. In order to explain trivalency of phosphorus, one of 3s electron is promoted to higher energy Sg3b orbital, so that has 5 unpaired electron excited state. This orbital are hybridized to give 5 sp3d hybrid orbital arranged in trigonal bipyramidal geometry. Then each of the sp3 hybrid orbital overlap with 2p orbital of fluorine, forming 5pf bond having trigonal bipyramidal geometry. It may be noted that d orbital involved in sp3 dehybridization in 3d Z2. It may be noted that in this geometry all the bond angles are not equal. Three bond the same plane making an angle of 120 degree to one another. These are called equilateral bond. Of the remaining two, one lies above and other lies below the plane of equilateral bond making an angle of 90 degree with the plane. These bonds are termed as axial bond. It has observed that axial bonds are slightly longer than the equatorial bond in geometry. Example, in case of PF5 molecule, each PF axial bond 2.19 angstrom and each PF equatorial bond 2.04 angstrom. This can be explained in terms of repulsive forces between electron pair due to different bond angle. Let us count the repulsive interaction of an axial equatorial electron pair as shown in figure. The electron pair of axial bond is being repelled by 3 electron pair at 90 degree and one at 180 degree.